Welcome to the Blueprint Room. I am your chief architect for today's high-rise exam construction blueprint workshop, and we are going to look at a quote straight from the source material that should be written on the wall of every math classroom. Most students lose easy marks on trigonometry, but after this explainer, you won't be one of them. We are dealing specifically with the Cambridge AS and A-Level Mathematics 9709 syllabus today, zeroing in on trigonometry graphs of sine, cosine, and tangent. Listen, right now, across the globe, thousands of students are building their exam answers on incredibly shaky foundations. They treat their exam paper like a blank page to just scribble on, instead of what it really is, a highly structured construction site. We are not just going to memorize a few formulas today. We are going to act like elite structural engineers. We are going to look exactly at the building regulations required by the Cambridge examiners, lock in those core concepts, and construct the kind of high-yielding, load-bearing answers that easily withstand the most rigorous examiner stress test imaginable. Let's get our hard hats on and dive right into it.
Welcome to the Explainer. Today's deep dive is all about constructing our high-rise blueprint for trigonometry graphs. When you pore over the Cambridge Principal Examiner reports, a massive structural failure becomes obvious. Students almost always fall into one of two traps. Let's look at our builder profiles to understand this. Builder number one, let's call him Alex. Alex works incredibly hard, but he acts like a machine that just stacks up massive, heavy bricks of raw mathematical facts. He memorizes every single coordinate of a standard sine wave, every single period, every amplitude, but he just dumps these heavy bricks onto the page without ever checking if the steel frame of the question can actually support that specific weight in that specific context. The structure becomes way too rigid, the foundation cracks, and the answer collapses. Then we have builder number two. Let's call her Sam. Sam is all about the aesthetics. She wants to put up these beautiful, shiny glass panels and decorative features. She uses fancy mathematical terminology and writes beautifully formatted but entirely superficial conclusions. She completely misses the core command words. There's no foundational math cementing her arguments together. It looks nice from the outside, but one tap from the examiner, and the whole glass facade shatters. By looking closely at the syllabus framework today, we are going to fix both Alex's and Sam's approaches, turning them into master builders.
Here is our construction schedule for today's explainer. First, Phase 1, the groundwork, laying down the core principles. Second, Phase 2, erecting the frame, which is our technical methodology. Third, Phase 3, building the analysis, diving deep into critical evaluation. And finally, Phase 4, the site inspection, where we go over the top examiner warnings.
Let's start laying the concrete with part one, the groundwork, covering our core principles. Okay, what is absolutely crucial about this slide is how it translates the exact assessment objectives into practical structural demands. Look at the left column here, theoretical architecture. The syllabus explicitly states that the foundation of trigonometry rests on precise definitions, causal relationships, and cross-topic integration. The examiner reports continually, and I mean constantly, highlight that candidates who reference cross-topic connections achieve significantly higher marks. It is literally not enough to just know what a sine graph looks like in total isolation. You have to connect it to the wider math landscape. If you just drop a graph on the page without showing what causes the transformations, you're building a house with no mortar. Now look at the right side, academic benchmarks. This is where we see logical reasoning and a massive emphasis on analytical depth over superficial breadth. When an exam question, say a high-tariff past paper challenge on the drafting screen, uses a complex command word like evaluate, it is demanding a fully evaluative structure. Think about Alex for a second. If Alex simply lists the periods and amplitudes, which is a purely descriptive approach, he misses the mark entirely. He builds a descriptive shed when the examiner asks for an evaluative skyscraper. Top-performing students exhibit a connected conceptual understanding. They don't just know the math, they know how the math holds the building up under pressure.
Let's move straight into Phase 2, erecting the frame, focusing purely on technical methodology.
So the single most critical point on this slide, the literal iron framework of our entire system blueprint, is the method mark strategy. You have to understand this deeply. This is a foundational assessment principle where marks are explicitly awarded for the process and the systematic reasoning, not just the final numerical answer. Think of it as the examiner rewarding you for making your step-by-step construction process completely visible on the blueprint. If you just scribble down the final answer and it happens to be slightly off due to a tiny arithmetic error, the entire building collapses. You get 0 points. You lose all those underlying method marks. On the flip side, what does Sam do? Sam just describes what she plans to do in beautiful sentences without actually executing the mathematical calculations. That won't earn you points either. The method mark strategy dictates that you must create a transparent, easily traceable path of systematic reasoning.
You are showing the examiner the exact load-bearing columns you erected to get from point A to point B. If the examiner can't see the columns, they assume the building is unsafe. It's really that simple.
And this slide brilliantly illustrates exactly how we build out that systematic reasoning, column by column. This is the exact 5-step standardized sequence you need to process and answer sine, cosine, and tangent graph questions. Step 1. Deconstruct the question. You have to locate the command words. Are they asking you to sketch, evaluate, or solve? That's your zoning permit. Step 2. Extract relevant data. Sourcing your raw materials, your boundaries, your domains, your specific equations from the provided text. Step 3. Select the analytical framework. Are we dealing with an amplitude shift, a phase shift, an asymptote calculation? You have to pick the right crane for the heavy lifting. Step 4. Execute with clear notation. Make sure your mathematical workings are clean, visible, and structurally sound. And finally, Step 5. Present with correct terminology. Following these 5 steps in exact order ensures you don't skip the vital analytical stage before presenting your final answer. If you skip a step, you leave a gaping hole in your floor plan.
Now for Phase 3, building the analysis. This is where we get into critical evaluation, the real heavy ironwork of your exam. Let's look closely at this text comparison because this is where the real ironwork peer debate happens. Comparative analysis in trigonometry graphs requires identifying both similarities and differences. Let's imagine Alex and Sam at the drafting board right now, arguing over how to construct a model response paragraph. Alex wants to fill the whole paragraph with a massive cement block of terminology and raw definitions. Sam is arguing that without a hollow space for a dynamic counter-argument or a comparative point, the structure has zero flexibility to hit those top-band scores. And Sam is actually right on this one. It's fascinating how the examiner notes explicitly specify the need for comparative connectives, supporting each comparison with evidence, and drawing conclusions about relative importance. For instance, if a question asks you to compare a translated sine wave to a standard cosine wave, Alex can't just list the coordinates of both. He needs to identify how the phase shift of the sine wave might align its peaks perfectly with the cosine wave. That's a structural similarity. But then he must point out the differences in domain restrictions provided in the context. You have to use structural connectives like whereas, conversely, or in direct correlation to. Those words are the rivets that hold the iron beams together. Then you lock it all in by drawing a conclusion about why those mathematical features actually matter.
Which brings us perfectly to the core metrics for evaluating evidence quality. If you want a top band score, your mathematical argument has to survive in the real world. You absolutely have to identify limitations. For example, what are the structural limits of the tangent graph in this specific given domain? Where are those asymptotes acting as literal walls you cannot cross? You must identify assumptions made. Are we assuming standard, unchanging conditions in this mathematical model involving a sine wave? Note alternative interpretations, and crucially, assess the effect of all this on your final conclusions. If your argument doesn't acknowledge its own structural limitations, it simply will not hold up under the examiner's rigorous criteria. It's like building a skyscraper without accounting for wind resistance. It might stand up on paper, but the moment the examiner applies pressure, it snaps.
And that brings us to Phase 4, the site inspection. It is time to look at the top examiner warnings directly from the Cambridge reports.
Site inspection time. Before we secure this high-scoring paragraph framework and pour the final layer of text concrete, we need to make sure your construction line is permanently reinforced. So right now, subscribe to Ace the Exams at the handle @AceTheExams and turn on all notifications to receive our weekly structural grade upgrades. Whether you are building an IGCSE foundation or setting up a towering A-level skyscraper, this channel is your primary grid. Okay. Let's look at warning number 1 from the examiners: wrong approach, wrong context. This is a classic, catastrophic trap in trigonometry graphs. Students memorize the perfect shape of the sine, cosine, and tangent graphs, but when the context of the question shifts, let's say you're modeling the tidal patterns of a harbor over a 24-hour period, they blindly apply a standard 360-degree algebraic approach without contextualizing the domain or the real-world time constraints. They use the wrong material for the specific environment. If you use a non-contextualized formula in a real-world modeling question, your evidence beam completely fails to latch onto the main theses column. You miss the entire core of what the question is assessing.
Warning number 2, ignoring format and presentation conventions. The examiner reports note that this structural failure happens all the time. The presentation of mathematical information must follow strict conventions, proper headings, correct terminology, appropriate formats, and incredibly clear annotation. A student might draw a mathematically flawless tangent curve, but if they fail to use a ruler to draw the asymptotes, if they forget to clearly label the axes, or if they don't explicitly write down the coordinates of the intercepts, they lose marks. Listen, those aren't just aesthetic choices. That is vital mathematical annotation. Think of it like the Peel methodology in essay writing.
point, evidence, evaluation, link. In math, your format is your point and evidence. You are riveting your data to your evaluation. If the examiners cannot clearly see your physical process mapped out, they cannot award you the method marks. Your cement is basically just wet sand.
Warning number 3. Answers are not specific to the context given. Generic answers lacking context-specific application will cost you heavily. It is so heartbreakingly common to see a beautiful, complex calculation of a period shift that ultimately fails to answer the question because the student didn't link it back to what that period shift actually meant in the context of the problem. You have to explicitly link your mathematical data directly back to the evaluative context. You must physically write the sentence that connects your mathematical output, like a calculated change in amplitude, back to the specific real-world scenario or the theoretical constraint the examiner originally asked about. If you don't do this, it's like building an elevator that doesn't stop at any floors. The mechanism works, but it's completely useless to the building.
Now we are entering the interactive viewer rebar stress test. I want you to look at this examiner alert. Principal examiner reports reveal that candidates consistently confuse key terminology. You must always define your key terms before using them in extended responses. Let's do a quick blueprint matrix test right now. Imagine a 60-second countdown timer flashing on your screen. If you are talking about amplitude, period, frequency, or translation, what is the single most high-yielding core metric needed to define them? You need to be precise. Do not assume the examiner knows what you mean if you use a vague description. Saying the graph moves up is mathematically incredibly weak. Saying the graph undergoes a translation of positive vector 0a is precise, accurate, and structurally sound. Precise terminology is exactly the rebar that holds your mathematical concrete together. To ensure these definitions and frameworks stay locked in your head, the source material suggests an amazing memory hack. Using a visual story method to encode these sine, cosine, and tangent graph concepts. Don't just look at abstract lines on a Cartesian plane. Relate them to standard physical visual models. You can map the sine wave to a cyclical journey starting at 0, building up to a maximum height. A cosine wave can be mapped to an object starting at a maximum peak and descending down. The tangent graph visually represents approaching an invisible, impenetrable barrier, the asymptote, but never quite touching it. When you associate these abstract mathematical principles with clear physical visual models, it completely prevents you from confusing the shapes and properties when the pressure of the exam timer is counting down and your mind starts to race.
So, we have thoroughly laid down the groundwork. We've erected the technical methodology, we've built out the critical evaluation, and we've survived the top examiner site warnings. The next time you sit down to solve a Cambridge 9709 trigonometry graph question, I am challenging you directly. Map out that 5-step framework before you write a single number. Force yourself to identify those command stress points. Will your next answer just be a pile of memorized facts crashing to the floor, or will it be a highly structured, load-bearing analysis that directly answers the context of the question? Keep these examiner insights at the front of your mind. Treat your exam paper like a true blueprint, and you will absolutely be on your way to securing those top-band marks. Thanks for joining the workshop, and I'll see you on the next build.